in the adjacent figure, which shows a similar situation. But this time, the external agent gives a continuous periodical sinusoidal up and down jerk to one end of the string, oscillating about their equilibrium. Mean position is the pulse or wave passing through them. The oscillations are normal to the direction of wave motion along the string, so this is an example of transverse wave. We can look at a wave in two ways. We can fix an instant of time and picture the wave in space. This will give us the shape of the wave as a whole in space at a given instant. Another way is to fix a location, that is, fix our attention on a particular element of string and see its oscillatory motion in time. The adjacent figure describes the situation for longitudinal waves in the most familiar example of the propagation of sound waves. A long pipe filled with air has a piston at one end. A single sudden push forward and pull back of the piston will generate a pulse of condensations, that is higher density, and rarefactions, lower density, in the medium, that is air. If the push-pull of the piston is continuous and periodic, that is sinusoidal, a sinusoidal wave will be generated propagating in air along the length of the pipe. This is clearly an example of longitudinal wave. The waves considered above, transverse or longitudinal, are traveling or progressive waves since they travel from one part of the medium to another. The material medium as a whole does not move, as already noted. A stream, for example, constitutes motion of water as a whole. In a water wave, it is the disturbance that moves, not water as a whole. Likewise, a wind, motion of air as a whole, should not be confused with a sound wave, which is a propagation of disturbance in pressure density in air, without the motion of air medium as a whole. Mechanical waves are related to the elastic properties of the medium. In transverse waves, the constituents of the medium oscillate perpendicular to wave motion, causing changing its shape. That is, each element of the medium is subject to shearing stress. Solids and strings have shear modules. That is, they sustain shearing stress. Fluids have no shape of their own. They yield to shearing stress. This is why transverse waves are possible in solids and strings under tension, but not in fluids. However, solids as well as fluids have bulk modules. That is, they can sustain compressive strain. Since longitudinal waves involve compressive stress or pressure, they can be propagated through solids and fluids. Thus, a steel bar possessing both bulk and shear elastic moduli can propagate longitudinal as well as transverse waves, but air can propagate only longitudinal pressure waves, that is sound. When a medium such as a steel bar propagates both longitudinal and transverse waves, their speeds can be different since they arise from different elastic moduli. Displacement relation in a progressive wave. For mathematical description of a traveling wave, we need a function of both position x and time t. Such a function at every instant should give the shape of the wave at that instant. Also, at every given location, it should describe the motion of the constituent of the medium at that location. If you wish to describe a sinusoidal traveling wave, the corresponding function must also be sinusoidal. For convenience, we shall take the wave to be transverse so that if the position of the constituents of the medium is denoted by x, the displacement from the equilibrium position may be denoted by y. A sinusoidal traveling wave is then described by y of xt equal to a sine into kx minus omega t plus phi. Equation 15.2.